Today I'm going to talk about the consensus halving problem for sets of items. This is joint work with Paul Goldberg, Ayumi Garashi, Basin Manurangsi, and Varut Suksampong. So what is the consensus halving problem? It's a fair division problem where we have a resource that's modeled as the 0-1 interval. You can think of this as a cake or as a piece of land. It doesn't matter as long as it's something that can be modeled as an interval. And there are n agents, and every agent has a different opinion about which parts of that resource are more valuable and how valuable they are. And this is modeled by having a valuation function for every agent, which basically tells us for every subset of the interval what value the agent associates to it. In this simple case, we're looking at densities. So basically the blue blocks you see are the density function of the first agent, and this the interpretation here is simply that the amount of value that an agent has for a subset of the interval is the amount of blue volume, and analogously for the second and third agent. And what is the goal in this problem? So the goal is to find a consensus halving. A consensus halving is a partition of this interval into two parts that we denote by I plus and I minus. And what should they satisfy, these parts? Well, it should be such that all agents agree that the two parts have the same value. In other words, for every agent, the value that they have for the part I plus is the same as the value for the part I minus. So in that sense, that's where the name comes from, consensus halving. There is consensus amongst the agents that you have halved the resource into two parts that have the same value. What is the motivation for this problem? Where you can think of, for example, two families that want to divide some resource, and you want to ensure that all the members of both families are happy with that division, that they agree that it's a fair division, that the two parts have the same value. Let's start with some examples to get a better feeling for the problem. So in this first example, the three agents all have the same valuation functions. In other words, they value the resource in the same way. In that case, it's very easy to find a consensus halving. You just cut the resource through the middle of the valuation function, and the two resulting parts have the same value for all three agents. So in that case, we just had to cut the resource in one place. Now let's see what happens with a more complicated example. So in this case, we again have three agents. The first agent has this valuation function, the second one has the green valuation function, and the third agent has the red valuation function. And as you can see, they value the resource differently. Now, if we go and put a cut over here, if we cut the resource over here, then the two resulting parts, namely this one and this one, they have the same value for the first agent, for the blue agent. They have the same value for the green agent, namely the second agent. But the third agent does not agree that the two parts have the same value because there's more red volume on the left than on the right. So what can we do? Well, there's an easy way to resolve this by cutting the resource at a second point, namely adding a cut over here, and considering the partition that is, on one hand, the middle section and the union of the left and the right section. In other words, the two parts at the extremes and the middle part. And here you can see that clearly the first agent and the second agent, they're both still happy. And now the third agent is also happy with this partition because the amount of red volume in the two parts is the same. So here we had to use two cuts. Can it get worse than this? Yes, with three agents, it's very simple to create an example where we need three cuts. Simply have the agents value different parts of the resource. And in this example, you have to put a cut through every one of those blocks. In other words, you have to use three cuts. You have to cut the resource in three parts and in three positions, but still in two parts. And the reason for this is simply that if you don't cut one of these blocks, then the whole block will be either in I plus or in I minus. And as a result, that agent cannot possibly be happy with that partition. Obviously, the valuations can be much more complicated than this. Can we always get away with 3 cuts in this case, or can it get any worse? And so the consensus halving theorem tells us that yes, we can always get away with at most n cuts, with cutting the resource at most n places, where n is the number of agents. So however complicated the valuations are, this is a very general result, you can always get away with n cuts. And the way this is proved is by using a topological fixed point theorem, which is quite famous, the Borsuk-Ulam theorem. Now, the Borsuk-Ulam theorem allows us to prove that there exists a consensus halving that uses at most n cuts, but it doesn't tell us how to find it efficiently. So from a computational perspective, obviously we would like to know whether this can be computed easily or not. The first question one might think of is, let's try to find the consensus halving that uses the least number of cuts, the best consensus halving in a certain sense. And it's not too hard to show that this is actually NP hard, so that's too much to ask for. The next best thing is, well, since we have this consensus halving theorem that tells us it's always possible to find a solution that uses at most n cuts, let's ask for any such solution. Find any consensus halving that uses at most n cuts. And this is what is usually referred to as the consensus halving problem. Now, the interesting thing about this problem is that it cannot be NP hard unless NP equals co-NP. In other words, it's unlikely to be NP hard. And let me quickly explain why. So the reason is that the consensus halving problem lies in the class TFNP. The class TFNP is the class of all total NP search problems. So what are these total NP search problems? First of all, they're search problems. In other words, they're problems where you're looking for a solution, not decision problems where you're looking for a yes-no answer. Then they are in NP in the sense that given any candidate solution, in polynomial time, you can decide whether it is indeed a solution or not. And finally, they are total, which is very important. Namely, for any instance, there always exists a solution. And for the consensus halving problem, this totality is guaranteed by the consensus halving theorem. There always exists a consensus halving that uses at most n cuts. So what's special about these TFNP problems? Well, the first thing is that no TFNP problem can be NP hard unless NP equals co-NP. As I mentioned, this is not too hard to show, but it means that basically you should not be aiming for NP hardness. It's unlikely that any TFNP problem is NP hard. And the second point is that it's also not believed that there are any TFNP complete problems. So what can you do to provide evidence that some TFNP problem cannot be solved easily, is not polynomial time solvable? So what was proposed by Papadimitriou almost 30 years ago is to investigate the insides of TFNP, namely understand how problems in TFNP relate to each other, organize them into classes, prove completeness results, and in that way be able to provide evidence that, oh, that problem is not likely to be solvable in polynomial time, because otherwise we could solve all these other problems that we believe are hard also in polynomial time. So here I've put some of the main classes. The most famous ones are PPAD and PLS. PPAD is mostly known because the problem of computing in Nash equilibrium is PPAD complete. PLS has various local search problems that are complete for it, including finding a local max cut. PPP is related to the pigeonhole principle, and PPA is a class that's, in a certain sense, embodies parity arguments. And here for our problem, what's important is that the Borsuk-Ulam theorem is complete for this class. And this is important because since the consensus halving theorem is proved by using the Borsuk-Ulam theorem, this basically shows that the consensus halving problem lies in PPA, in this class PPA. But obviously, it could be easy. It could be in P. It could be in PPAD. And what Filos Ratsikas and Goldberg showed recently is that this consensus halving problem is actually PPA complete. So it's complete for this class PPA, which has at least two consequences. From a mathematical standpoint, it means that the consensus-halving theorem is as strong as the Borsuk-Ulam theorem itself. In other words, you can prove the Borsuk-Ulam theorem if you know that the consensus-halving theorem holds. And from a computational perspective, this tells us that the consensus-halving problem is unlikely to admit a polynomial time algorithm. And the reason for this is that, well, if it did admit a polynomial time algorithm, then all the problems in PPA would also be solvable in polynomial time, including all the problems in PPD, including finding a Nash equilibrium, etc. So this is the end of the first part of the presentation, which was about the classical consensus-halving problem as it has been studied up to now. And in this paper, what we do is we consider a different version of this problem. We consider the consensus-halving problem for sets of items. So what do we mean by this? Instead of having one resource, one interval that we want to divide into two parts so that everyone agrees that the two parts have the same value, what if we have multiple items instead? So for example, a house, a bicycle, a factory, and we again want to do the same thing. We want to divide this set of items into two parts so that all the agents agree that the two parts have the same value. So how do we model these items? Well, we basically model them as homogeneous divisible items. Let me briefly explain what we mean by this. So first of all, the items have to be divisible, otherwise it's easy to see that you might not be able to find a consensus halving, it might not exist. So we consider divisible items, which means that when you divide them into two parts, basically, you can have 50% of the item in one side, 50% on the other side, or 20% on one side, 80% on the other side. And the items are homogeneous. What does that mean? It means that the value that you get from a fractional part of the item only depends on that fraction. It only depends on what fraction of the item you get. It doesn't matter whether you get the left part of the item or the right part of the item. It's just how much of the item you get that determines the value you get from it. So in terms of, you might ask, well, what does it mean to divide a house into two parts or a bicycle? And obviously it doesn't make sense here to actually cut them in two. So what is mean by divisible here? It can be interpreted as sharing the resource, for example, or selling the house and then dividing the money that you got from this accordingly. So there are various ways to interpret this divisibility. So first, we'll consider just additive utilities. What are additive utilities? It's basically the simplest kind of utility you can think of for divisible items. Every agent has some value for the whole item, for every whole item. And how do you determine what the value is for a fraction of the item? Well, if you have 20% of some item, you simply get 20% of the value of the whole item. If you have 70% of some item, you simply get 70% of the value of the whole item. And then you are additive over items. So you do this for every item and you sum it up, and that's how the utility is determined. So it really is the most natural, the most simple utility you can think of for this setting. So first question is, okay, how many cuts can we possibly need to find a consensus halving in this setting? And it's easy to see that if you cut every item in half, you immediately obtain a consensus halving. The issue is that ideally you don't want to cut too many items because they are items, so dividing them is not something very natural or very nice. So you want to limit how many items you're going to have to actually divide. And so there is a better result, which is that you can get away again with at most n cuts, in fact with at most n items cut, where n is the number of agents. And this is very easy to show. Just put the items on a line, interpret them as an interval resource, and use the consensus halving theorem. And that immediately tells you that you're going to need at most n cuts. And as a result, you cut at most n items. Note that if you have two cuts within one item, then this just means that you can replace it by one cut because we have homogeneous items. Okay, so what this tells us basically is that we again have an upper bound of the number of cuts that we're going to need. We can always get away with n cuts. Can we do better than this? And again, in this case, it's easy to show that in the worst case, you might have to use n cuts. You might have to cut n items. Actually, we show a stronger result than this. We show that instances that admit a consensus halving with less than n cuts, strictly less than n cuts, are very rare. What do we mean by this? In what sense? Well, if you draw the utilities, the utility that every agent has for every item, if you draw those independently at random, then you're going to need n cuts for any consensus halving with probability 1. In other words, with probability 1, every consensus halving for that instance will require at least n cuts. And the last thing that's also easy to show is that, again, it is again NP hard to compute a consensus halving that uses the least number of cuts, just as for the original classical problem. But obviously, this leaves one question, which is, what about the consensus halving problem in this setting? Namely, what about computing any consensus halving that cuts at most n items? What is the complexity of this problem? And recall that this problem is the one that was PPA hard for the classical problem. And here, surprisingly, this problem turns out to be polynomial time solvable. In other words, we can, in polynomial time, compute a consensus halving that cuts at most n items when the utilities are additive. And the idea is quite simple. Let me briefly explain that. So let xj denote the fraction of item j that goes to part I plus. Then the partition I plus I minus is a consensus halving if and only if the following system of linear inequalities and equalities is satisfied. So let's take a quick look at this. The second line just tells that xj has to be between 0 and 1 for all j. In other words, the fraction of every item should be something between 0 and 1. So it's just to ensure that it's well defined. And the first line is the interesting one, which says that these two things should be equal for every agent. And what are these two things? Well, these two things are simply the value that agent I has for I plus on the left, and on the right, the value that agent I has for I minus. So this first line just encodes that for all agents I, they should believe that the two parts have the same value. And the important thing here is that this is a linear system of linear inequalities and equalities, which means that it's a polytope. So the set of all consensus halvings is a polytope. Obviously, we don't want to find any consensus halving. We want one that uses at most n cuts. And the key observation here is that any vertex of this polytope has at most n non-integral xj's. In other words, if you take any vertex of this polytope, at most n of the xj's will not be 0, 1. At most n of them will be truly fractional, strictly between 0 and 1. And what does this mean for the consensus halving, for the corresponding consensus halving? It means that at most n items will be fractional, at most n items will be cut. So that tells us that the only thing we actually need to do is find a vertex of this polytope. And this can be done in polynomial time. For example, you can just solve NLP to do this. This is a bit of an overkill. You can do it with a simpler methods. For example, there's a polytope algorithm, as we call it, that simply starts at some point inside the polytope and then moves in some direction until it hits the boundary, and then it moves in some different direction until it hits the boundary there. And you can show that in polynomial time, this is going to find a vertex. But the important message here is that, unlike in the classical problem, here you can actually compute it in polynomial time. Consensus halving that cuts at most n items. And obviously, this is for additive utilities, as I mentioned. What happens if you consider more general utilities? So let's recall what additive utilities actually correspond to. So what are additive utilities? Basically, it's depending on the fraction of the item that you consider, the utility that you get depends linearly on it. So this is what's shown in this graph. If you have 20% of an item, you get 20% of its value. If you have 70% of an item, you get 70% of an item, of the value of the item. And that's it. And as we saw on the previous slide, this problem, in this case, for these kinds of utilities, the consensus halving problem can be solved in polynomial time. So what we do next is we consider slightly more general utilities, actually the simplest, more general version that we could think of, which are what we call symmetric threshold utilities. So what are these utilities? For every agent and for every item, you have a cap, Cij. This is how we denote it. And let's think of this cap as being 0.1, in other words, 10% for this example. The interpretation is that if you have less than 10% of an item, it's as if you didn't have the item at all. You get zero utility out of it. And symmetrically, if you have more than 90% of an item, it's as if you already had the whole item. Namely, you get the same utility as if you had the whole item. This is represented in the graph, the bottom graph, where you can see that up to 10%, namely 0.1, the utility stays at 0. Then it starts going up linearly. And when you reach 90%, the utility does not grow after that. It stays the same. So what we show for these symmetric threshold utilities is that finding a consensus halving with at most n items that are cut is already PPA-D hard. So by considering utilities that are just slightly more general, the problem already becomes intractable, at least as hard as computing a Nash equilibrium. Before we finish, let me mention a generalization of consensus halving, which is quite interesting, which we call the consensus k-splitting problem. So this is a generalization of consensus halving in two directions simultaneously. First of all, instead of dividing into two parts, you now divide into k parts for any k, for example, 3 parts, 4 parts, 5 parts, whatever you want. And you also look at divisions into specified ratios, not just equal parts. So if you think about consensus halving, you're dividing into 2 parts so that all the agents agree that the 2 parts have the same value. But what if you want to divide them into 2 parts so that everyone agrees that the first part has twice as much value as the second part? That's a different problem. And so the way you can think of this is that you're given ratios alpha 1 to alpha k that sum up to 1, and you want to divide the resource into k parts so that all the agents agree that the first part has value alpha 1, the second part has value alpha 2, etc. And consensus halving corresponds to the special case where k is equal to 2 and alpha 1 and alpha 2 are both equal to 1/2. So we consider this problem for additive valuations, again, the simpler case. And what we show is that the polytope algorithm can be generalized to this case. And again, in polynomial time, you can compute a solution where here you are going to cut at most n times k minus 1 items. So this is the upper bound that we get here. And what we show is that in the worst case, you might actually have to cut that many items. So it's tight in that sense. And this worst case lower bound, it's not trivial and it's quite strong because we show that for any ratios alpha 1 to alpha k, we can construct an instance where you have to cut at least n times k minus 1 items. An interesting thing to note here is that there's no general existence result known for the consensus k-splitting problem, even in the original interval version. So our algorithm here in particular also shows existence that there is a consensus halving that uses at most n times k minus 1 cuts for additive evaluations. So let me just mention some open questions now. So the first one is, okay, so we showed that consensus halving with symmetric threshold utilities is PPA-D hard. And because, as we saw, is a special case of the original problem, it also lies in PPA. But there is a gap there, right? So is this problem PPA-D complete or is it PPA complete? Is it as hard as the original problem or is it equivalent to Nash equilibrium? There's a gap there that we don't know which way it will go. And the second question that I want to mention is the consensus k-splitting problem that we saw on the previous slide. So we had these results for additive utilities. What happens if you consider more general utilities, namely monotonic utilities? So as I said, there's no general existence result there. So first question is, if you have monotonic utilities, do you still have that there exists a consensus halving that uses at most n times k minus 1 cuts? Yeah, so that's it for this talk. Thank you for your attention, and I'll be happy to answer questions.